Hello, everyone, and welcome to Robot Design and Construction Tips for Demo Days, the 2021 competition for Best Robotics. Note that all of this information is stored online as well as the rest of the kickoff presentations, and you can access that with your Best National Registry account. Just make sure that you go to the correct link. You can also find all of the Q&A session breakouts and a lot of other additional resources, which if you're viewing this video, you probably have already seen. But just as a reminder, you're able to access all of that virtually. So, my name is Dakota Mann. I'm a Best Robotics alumni and currently a systems engineer at Lockheed Martin. And I will be going over a number of robot design and construction tips to aid your team during the competition with this year's consumable kit. So, we'll jump right in. An overview of what I'm going to be presenting today. I'm going to be talking about the engineering design process, what it is for those that aren't aware, and a refresher on why it is helpful for us as engineers and for creating your robots, as well as ways that you can apply it to processes outside of just robot construction. In addition to that, I'll be talking about subsystem and system integration. This is something that I do for a job, but the level that I do it at is not necessary for this robotics competition. So, how can you apply it in a way that is helpful for a smaller scale system, such as your robot? And also the communication and documentation that goes into that integration. Something that is extremely important for us in Best Robotics because of how many things have to be recorded and then later presented as part of some of your scoring material. In addition, some overviews over design, engineering, and math examples. This is something that is very difficult for new teams and teams that do not have as much experience with engineering, and simple ways that you can apply mathematics and physics to quickly decide whether something is going to work or not without having to build it at all. With the limited time that you all have to build and construct your robots, being able to apply some of these concepts before you cut any wood or bend any metal can be extremely valuable. And we want to make sure that all teams have a similar playing field when it comes to this. And finally, what many of you are probably here for, a couple of construction tips for how to best utilize the materials given to you in the consumable kit, as well as how to be safe with them and make sure that you are getting the best possible components out of this base material. We're going to begin with the engineering design process and why it's important. So, at its core, the engineering design process is basically a system of thought to make sure that whatever you are trying to design, engineer, or create has gone through the proper rigor so that it works the first time. And if not first time, how you can make sure that it works the second, third, or fourth time. You can actually use the engineering design process for anything, anytime that you want to create something. You just got to tweak the components a little bit. It's basically just how do you solve a problem. And this can be helpful for your robot, individual components, and is definitely something that the best robotics judges want to see in your documentation. So this includes the engineering notebook, this includes the marketing presentation, and this includes any additional presentations or discussions you may have about how you designed your robot. So having this whole thing planned out and plotted out and how that you actually came to the solution that you chose is extremely helpful to you. So make sure you record as you go. And part of the process is including objectivity in your design decisions. It can be very easy if you are the most outspoken member of your team to push forward the idea that you believe is best. And not this isn't always the best solution. So processes like the engineering design process help ensure that we're picking the solution that is best for the team rather than the one that we think is the best. So here is one depiction of the engineering design process. There are many, and it could be drawn in multiple different ways, but I will be going over this one because it's a bit more in depth. You can simplify it or expand upon it. You can use whatever variation of a system makes the most sense for your team. So, step one is, believe it or not, the most important step, but is also the step that is most often overlooked because it's the planning step, it's the preparedness step. And it's the step before all of the brainstorming and building, which is what a lot of us jump to, especially when we think we know what the answer is. So, part of step one is reading the rules, determining the requirements, and assessing what your situation is. This is the most important step because it sets the stage for everything else. By evaluating what is possible, what you're capable of achieving, and what requirements your solution has to fit within, it defines all the steps following it. And if you don't have a good baseline in step number one, you will often have to come back here after perhaps the testing or the evaluation step because the baseline wasn't properly determined. So, as part of this, I recommend making sure that you read the entire rules before beginning your brainstorming steps. This is to make sure that an idea that perhaps is very creative or is very effective isn't later on determined to be against one of the many rules that Best Robotics has outlined for us. So, read the full rules, make sure you fully understand the challenge and what's expected of you before you go on to step two. Step two is also very important. It's the brainstorming step. This is when we come up with as many different solutions as we possibly can to whatever it is that we're trying to solve. So, by understanding the problem, we can then come up with solutions that will solve it. At this stage, volume is often more important than quality. Ideas tend to build off of themselves, and as more and more ideas are proposed, they may cause you to think of other ideas or add ons or ways to build upon the ideas already brainstormed. Quality will come later, but for now, we want to make sure that we have all of the solutions we can think of. We want to make sure that we leave nothing behind and we have everything that could possibly be applied to this solution. So sometimes having fun with it is part of the process, making sure that you allow every idea in, no matter how crazy or initially ridiculous seeming, because you never know when another idea is going to build off of it. Step three is when we take these large amount of ideas generated before in step two and narrow them down into the ones that are actually effective to us. So this is a step where we may remove some of the sillier or more outlandish ideas and focus on the ones that we feel are most effective. Part of this analysis can be objective or empirical. You may have some kind of scoring matrix or design decision excuse me, design flow decision matrix where you are deciding what ideas and what options you may go with based on a number of criteria. Or it may be as simple as I like this idea. I think it has merit. I would like to go forward with it. So you can use written or just critical thinking to decide on different ideas, or you can use prototyping as well. This is an effective way to figure out which ideas have merit and might be useful to you. Is building a test of concept, a version of the idea that is quick and dirty and proves that it will work without needing to spend a lot of time figuring out all the details or even making it pretty. This could be pieces of paper glued together, or cardboard, or very, very rough wood prototypes. Something that just gets the idea across and proves that it'll work. You don't want to spend a ton of time on these, but just enough that you give the idea the time that it's worth. You don't want to discount something out of hand because the prototype was built poorly and didn't prove the concept. So give each idea, its fair share, but don't spend too much time trying to make things perfect because that's what the real robot's for, right? Coming out of step three, we have a good idea of what our best idea is. We maybe have one or two we're still entertaining, but going into step four, we have a pretty good idea of what we want to go with. And this is when we take that final idea and flesh it out and improve it until it's actually a part for the robot. So, by designing parts better, you can create them faster. And now that you have a full idea of what the whole robot's going to look like, a lot of people can work on different components at the same time. So, the importance of going through these other steps before you get here is that you have a good idea of the full design of the robot. And there's a number of software tools that Best makes available that can make getting to this step easier. But going into step four, you want to be building your final robot. Finally, coming out of it, we have a step 6 in here, which should be a step 5. My numbering is a bit off, so I apologize. But a final step is bringing all your individual components together into a final system and testing it, making sure that it does all the things you wanted it to do in step 1. Whatever the game field component is, whatever maneuvering you have to do, whatever the challenge is, step 6 or 5 is when we're making sure that it actually meets those requirements. Does it pick up the ball? Does it pick up the rod? Does it spin in a circle? Does it follow this tape line? Whatever the challenge happens to be, this is the step when we're making sure that it does everything it's expected to do. Now, what happens if it doesn't? What happens if we have our final robot and something doesn't function as we expected it to, or doesn't do the job we created it to do? Well, that means we have to go back in the process. And depending on which step failed, we may have to just go back to prototyping and try one of the other ideas we had in mind, or perhaps we misunderstood the challenge entirely. The robot's too big. The robot doesn't extend far enough to grab the piece we needed to. We broke the rules in some way and have a non compliant element. We may have to go all the way back to step 1 and reevaluate all of our design solutions, which is why the steps before this point are so important. Because if you don't do one of these steps properly, you may be forced to repeat it. Now, one of the often forgotten steps is the one at the very end after testing. Once your system works, once your robot is functional and does the things you wanted to do, you're not actually done yet because you have to document everything that you've done. If you've created different documents or taken pictures and talked about the things you've done as you went through these steps, this is very easy. This is just collecting all of the things that you've created, all of the different design documents or brainstorming pictures that you've made and putting them all together. But if you didn't document as you go, you're forced to try and come up with why you made certain decisions. Why did we go with this idea over this other one? Why did we make this prototype? Or why did we discount this prototype and say it didn't work? By recording as you go, you can make this step very, very easy. And you can make things like your notebook or your marketing presentation or your descriptions in the exhibit that much easier. But speaking from experience, if you're forced to create these out of nothing when you reach the end, this can be extremely difficult and will not be as accurate as it would have been if you recorded as you went. So, highly recommend anytime that you are talking about elements of the robot or making decisions, make sure you record what that decision is and why you made it. What went into making that decision? What helped you decide on the specific part that you made? All of this will be very, very helpful to you in the future and will make your best experience that much better. Now we're going to get a bit into systems integration. Because of the way that best robotics challenges work, often the challenge proposed to us is difficult to a point where we can't accomplish all of it with only one part. Our robot has to drive, our robot often has to manipulate or pick something up. There's a lot of different parts that go into a best robot, and we have to make sure that all of them work together. So, on a bare bones scale, you will often have three main parts to the robot. You'll have the drive platform or the chassis, whatever your robot is utilizing to move around. So, this could be wheels, this could be skids, this could be a lot of different, uh, you know, components that allow your robot to move, depending on what the year looks like. And then we usually have some kind of end effector or manipulator, some way to interact with the game field and interact with the scoring pieces for that year. And often this end effector, this manipulator, has to be able to have a wide range of movement and often interact with a wide different variety of objects. Maybe this is two different parts, maybe this is four different parts. But in the end, however you are interacting with the game field is a very important part of the robot. And finally, you have programming and software. These components have to be able to be controlled by the controller and the driver and interact with the spotter in the years that there is a spotter. So, the way that you program your robot can either make all of the system work better together or can introduce new flaws and new problems that have to be solved. So, The better you integrate these three or more, in some cases, components together, the better your whole system will function together. And a big part of this system integration is communication. For a lot of teams, you have more than just one or two people working on your robot, you have many. And in order to make sure that that team is effective, you all have to be communicating and you all have to be on the same page. Since you have limited time, having one person build every component is time consuming and may not allow you to test or practice with your robot before competition comes, if you're able to finish it all. So, by making sure that all of your individual people are communicating well and are on the same page, you can avoid a lot of hiccups you have where some people may think that you went with idea or one prototype rather than another. Or some people who choose to do their idea rather than helping the rest of the group. So by making sure that you communicate within your team and making sure that everyone is talking and on the same page, you can avoid a lot of problems that you may not expect would come up. There's a lot of different ways you can do this. There's a lot of ways in industry that we accomplish this. The Scrum is one of this. It's part of a greater system. In short, it's like daily stand-up meetings. So at the start of every single meeting, you all talk about what you're planning to do that day, and make sure you communicate what problems you may be having and where you could use help. This quick 10, maybe 15-minute meeting at the very beginning of when you begin your workday is underrated and has a lot of value in making sure that people understand what everyone else on their team is doing and is getting the help that they require. So some of you may be meeting in person, some of you may be meeting virtually, and both of these present their own unique problems. But both ways of meeting and more require good communication for effective meetings. Part of that communication and documentation is recording some of the steps and some of the things you do, as I mentioned earlier. By recording these things, you can help look back, and when someone is wondering why a decision was made, because you recorded it, you have that information, and it can be a really good way to remember uh, previous problems that you solved to make sure that you don't repeat them. And as always, it is an important part of the notebook and other scoring elements. So make sure you're doing that because it will help you in the long run and will help you get a better score. Some of the things that are important to record are records of the process as you hit different milestones and as you move through things, the info shared between many different groups, requirements, as I mentioned in that step one, when you figure out what you want your robot to do. When you get to the final step in testing, it can be helpful to have a checklist of what you wanted your robot to accomplish. And as you go down the list and check each item, you can verify that yes, our robot did in fact do what we set out to build it for. And this is also very helpful for new people. Sometimes you'll have people join in the middle of a season. And if you have to have someone explain to them all of the steps you've taken up to this point, it takes valuable time. By having it all recorded somewhere, they can quickly get up to speed and understand what the rest of the team is doing. Or if someone just misses a meeting, they may miss something and there was an important decision made, and they want to make sure that you made the right decision. So by being able to read about why you made your decision, what the criteria were, what was your thought process going in, they can agree that the decision you made was the right one. Coming right back around to that important communication, the engineering notebook, which is a record of your process as construct and test your robot, is due on practice day, which is 2 weeks before game day this year. So make sure you get that in. You must submit an engineering notebook. Even if it's a handful of pages, even if it's not the full 30, make sure you get something in because otherwise you will not be able to compete. Uh, Something is better than nothing in this regard. And while you won't get as many points as if you put in the full work, whether you finished it or not, putting something in is necessary in order to compete. So make sure that your mentor is submitting that to the hub director and make sure that you get something in on practice day. So we're going to do a brief overview of math and torque. The example we are using is with some of the motors provided to you in Returnable Kit. and this will mostly serve as reference. There's a lot more math online about how you can apply physics to mechanics and help avoid some of the extra time spent on prototyping. But we're going to deal with a fairly simple example involving torque. Now, torque is basically rotational force. It is the weight being applied, in this example, by the motor in relation to the length of the object you are trying to move. So the way you often can figure out torque is the force in pounds applied by your motor times the moment arm, which is the length of whatever object you are trying to move. So for this example, we're looking at a fairly simple manipulator, a PVC pipe attached to some kind of device that allows you to, pick up a game field device and then the game field device itself. So in this example, we're using a waste cargo ball, which I believe was from the Warp XX competition. So this was in 2012. But this is all relevant because you don't have to just take into account the weight of your PVC pipe in your arm, but also the thing you intend to manipulate, which sometimes can be really light or sometimes can be really, really heavy. So here we have a couple of weights listed out. So we have the PVC pipe. We've determined probably through some kind of scale or weight that it's about 0.21 pounds for every foot of PVC pipe. And we have 24 inches, so it's about 2 feet. Then we have the grapple, as this is called it, which manipulates the waste cargo ball. And we've weighed that to be about half a pound. And then we have the waste cargo ball itself, which is about 0.4 pounds. So all of this together constitutes the weight that our motor is going to have to be able to rotate. And the higher the weight is away from your motor, the longer your moment arm is, the leverage of that weight will make rotating this harder and harder. So if we look at the next example, we've taken the length of the PVC pipe and we've multiplied it by its weight per foot. And we've done the same for the grapple and the ball and combined figure out how much, torque our motor is going to have to apply to be able to rotate this entire thing. So you'll notice the grapple has been multiplied by 2 feet, the ball has been multiplied by 2 feet, and we've got a foot-pound measurement for each one of these weights. So you'll notice that as things get farther away, even though the ball only weighs 0.4 pounds, when it's 2 feet away from our motor, it's actually as if it were experiencing a weight of 0.8 pounds. So that's where that moment arm begins to come into effect. So adding all of these together, we've determined that the total force our motor has to move is 2.22 foot-pounds. So now we can go check the spec sheet for the motor and figure out what it's able to move and see if we can actually rotate this device that we've created. And it turns out the large motor has a torque of 23.53 inch-pounds. So we've done a conversion here. We've calculated in feet, but the spec sheet gives us the information in inches. So we've converted the number and find that our torque of 2.22 foot-pounds, which is 26.64 inch-pounds, is a lot larger than the large motor torque is able to apply. So this design is probably not going to work. We're going to have to do something to change it to make sure our motor can rotate it. Whether we choose to gear our motor up so that we can lift a higher amount of torque, maybe we try and reduce the weight. We have a number of options available to us, but this design, as it is, will not work for us. So that's a quick example of how applying math like this means that we didn't have to build any of this. We didn't have to build the PVC pipe or the grappler or put a ball in it and test it to determine that this would probably not work. And we've saved a lot more time than we would have if we had tried to construct this. So that's how this can help make your process faster because time is so valuable and best. You have such a limited amount of time to be able to complete your robot. So anything you can do to save time is really valuable. Here's a quick overview of the different torques of the motors that you're given. So we have the servo, the small motor, and the large motor. So you can come back to reference it in this presentation, or you can reference the spec sheets, which we'll have a link to at the end. A couple of other components that you have in the kit that we're going to go over that are more complex, so they deserve an explanation, is you have a potentiometer, sometimes referred to as a pot for short. So a potentiometer basically allows you to measure rotation via a number of ticks on it. So this can be really helpful for your software and your programming because you can know the position of some kind of rotational piece. Some years this is more important than others, but some teams will also use this for autonomous code. Perhaps you want a single button that will put your arm in a very specific location. Or perhaps you have some kind of rotating piece on the front of your robot and you want it to be at a very specific angle and you want it to go to that angle every single time. Well, a potentiometer is a very effective way to do this, and it will be connected to the analog outputs on your cortex. So there's a lot of different materials and how you can wire one of these up, and they are in the consumable kit. So you are able to solder to these leads for a pretty permanent connection if you so wish. And you can see there's a couple of different links here on the presentation. Mentioning again that you have a digital version of this, so you can't access the links here in the video, but you can if you go into the presentation and open them. And they'll show you how to like wire it up and how to attach them. So I won't go over it too much here, but I will point out that the potentiometer only will rotate 300 degrees. So you can't put them on your wheels or anything that is going to rotate all the way around. 300 degrees is still a pretty significant range of motion, but it will not rotate fully. So if you try and force it past that, it will break. And potentiometers, while fairly sturdy when it comes to sensors, are still prone to damage. So make sure that when you mount these, you're mounting them securely and mounting them in the way that they're not going to break. It's not the hardest thing in the world to replace them, but still something to be thoughtful of. Here we have an overview of all the different software licenses available to you. There's a lot of different programs that you can use for programming, for actually programming your robot and putting the functions in, and a lot of ways you can use CAD software to visualize your robot before you actually create it. These are extremely helpful for if you're not sure if something will fit together, for your system integration, making sure that your manipulator fits on top of your drive platform, for example, or trying to figure out the finer elements of a manipulator that otherwise would be hard to do on paper. Lets you visualize things in 3D, and while there is a learning curve, it's very, very effective. And I've used it a lot to create something without actually having to build it and save myself some time. And as we mentioned, some of the math you've done up to this point, they also have a couple of math solutions that can make that math easier for you. So there's Mathematica by Wolfram Alpha that really helps you visualize your functions and visualize your math and can do some lower level functions for you. So I've used Mathematica a few times and it's been very, very helpful for me. So here's a couple of tools that are available to you. We'll have some more links at the end of the presentation to these. Right there. So there'll be some information for how to download it from the best national registry at the end of this. Now, the moment I'm sure a lot of you are looking forward to construction tips. What are the best ways to work with the materials given to you in the consumable kit? These are mostly recommendations, so some of the finer details I'll just leave up. They'll be for reference, not as much as helpful for me talking through like why does the drill press has to move this fast or whatever. So some of them will be for reference and some of them I will speak to. Starting with the materials contained in your consumable kit. So while some of these change year to year, uh, in general, these are the large components that you're going to be building things with. So you're going to have a polypropylene sheet and a polycarbonate sheet. So these are sheets of plastic of various thicknesses that will allow you to make components. A lot of aluminum. You have an aluminum bar, which is fairly thick, a big rectangle. Aluminum rod, and an aluminum sheet. The sheet is a lot thinner than the bar is, and is thinner than also the plastic sheets or the wood sheets. You also have a piece of steel all thread, which is along, basically if you took a bolt and extended it all the way out. It's threaded along the entire length, and it's made of steel. And you also have some piano wire. which is very good for bending into smaller components or attaching things to your servos. They can be bent and then poked in through one of the holes on the servo head, and makes it a lot easier to move things. There's also a selection of wood and plywood, a 1x4, and a dowel. All wooden components that make great base materials. They make great arm materials. There's a lot of different things you can do with the wood, and there's also some 3/4 inch thick foam insulation, which is a fairly rigid, very lightweight material that you could find a lot of different uses for. If you have something at the end of a long arm, using the foam board insulation, while not very strong, will reduce your weight significantly. And that might be helpful, as we saw in the torque calculations, if you're putting something directly on a motor. A variety of PVC pipe is included as well, T's and elbows and connectors for that, and a lot of hardware. So a lot of bolts, a lot of screws, a lot of nuts. And remember that only stuff in the consumable kit is what you're allowed to use in your robot. So no outside fasteners are allowed to be used, or tape or adhesive as well, just what's included in the kit. So starting off, we're going to talk about some of the plastic sheeting. So for the thinner sheeting, while all of this can be cut with saws, if you have the sheeting about 1/8 of an inch is the best recommendation here. You don't always have to cut through it to get a nice line. You can use a scribe. There's some glass cutting knives you can get from Home Depot that will work, or just a standard utility knife that allows you to score part of the sheet. You don't even have to go down all that thick, just enough so that that area is weaker than the area surrounding it. And if you put it up against a table edge, or you have like a 2x4 clamping it down, you can then push and snap part of the plastic sheet off. Which, if you do not have access to bandsaws or um, powered saws, can be a really easy way to cut it. Just make sure that when you score it or scribe it, you're going out down deep enough that you get a clean break. Otherwise, your edge can be really messed up. It won't give you a fine edge, or it might not break where you want it to, and it may shatter in a way that is not at all what you want. Most saws will cut through plastic just fine as well. So here's a couple of recommendations for specific blades you can use that will give you the best edge. Just be aware that if you are moving too fast, or you have a too fine of saw blade, the friction caused may end up melting your sheet a little bit. So, especially with the polypropylene. So just be mindful of that. Be careful. Try not to go too fast, but just fast enough to be able to get you through the material. Um, and you can come back and reference this if you are having trouble, and see if perhaps your blade is the issue. The aluminum bar and the rod is significantly harder to work with than the plastic. You can work with both of them with a hacksaw. The rod is easier than the bar in this regard. Um, Aluminum is a lot softer than steel, and so while it will be a tedious process cutting through it with a hand tool, it is very much possible. So you can do it if that's what it comes to. However, you can also use electrical saws to cut through it, and that will be faster and will usually give you a better edge. So you can do this with a jigsaw, a bandsaw, or a horizontal bandsaw. For the 1/2 inch bar on a bandsaw, you can use a wood blade because the aluminum is so thick, and it is aluminum. It is a lot less hard than something like steel. So you can use a wood cutting blade if that is what you have. You can also use a bimetal metal blade. That will work just as well. That will actually probably work a little bit better than the wood cutting blade. But if that's what you have, that will work. You just can't use it on any of the steel. And I wouldn't recommend using a wood blade on the aluminum sheeting, because it's thinner. Honestly, if you can avoid using a bandsaw for the aluminum sheeting at all, that is recommended, which I think is our next slide. Yep. It is not recommended, just because for bandsaws, you want to make sure that the number of teeth that you have on the blade, you usually want 2 or 3, um, for the height of the material. And even when you go to a metal bandsaw blade, you will usually not have enough teeth for the sheet itself. So there's a couple of other ways you can work with it. The main way being tin snips or powered snips. That is the easiest way to cut through the sheet, but that will often give you a rough edge, and that can distort the edge of the material as well. So if you are using it for something that you need it to be very flat, or you need the edge to be very nice, um, the best way to do that is using a hand tool like a hacksaw, or to use specific sheet metal machines like a press or a shear, and that will give you a really, really nice edge. However, if you don't really care if it's a little wavy or if you're intending to bend it later, Tim snips will work just fine. Same goes for bending. There's a lot of machines specifically designed to work with sheet metal, as well as hand tools do the same thing that can make bending your sheet metal easy. However, if you don't have access to these, you can put it in a vise and do the classic hitting it with a hammer or mallet to get the bend you want. Just be careful while you're doing it. If you do too sharp of a bend, you'll start to see some fracture lines on the edge, especially if you're doing a very tight bend. So you want to take your time with it. Don't hit it too hard. And try and do as shallow of a bend as you can get away with if you're bending it with a hammer. And try and get like the radius of the curve larger if you can too. So there's like you can put like a metal rod inside or even a dowel sometimes, and that can help give you that larger curve to make sure that you're not splitting or shearing it off as you try and bend it. Working with PVC is pretty easy. You can do it with pretty much any kind of hand tool. If you have a wood saw or even a hacksaw, you can cut through the PVC pipe very, very easy. And there's also specific tools that allow you to do that, like a PVC cutter, which is the one shown here. That will not give you a fine edge though. So if you are rough cutting some pieces of PVC pipe and just need them to be whatever length, it doesn't really matter. The PVC pipe cutter makes that very easy. If you're putting in a connector, you can also get away with it, but it will not give you a straight edge. So if you need a straight edge, a bandsaw or a hacksaw is a much better way to do that. And when you're drilling holes in that, it can be difficult to make sure the piece doesn't rotate. So if you put it in a vise or you have a way to clamp it, that's ideal. Um, but a drill press or just a hand drill are both good ways of putting holes in this and all the other materials we've mentioned so far. For anyone unaware, this is what a drill press looks like as opposed to a hand drill. It's got a table that you clamp your material to and a chuck that you put the bit in that you're using, and then you can drill into the material you've clamped onto the table. You want to make sure you don't drill into the table itself, which is why vices or other things that allow you to hold your material above the table are very, very helpful. The biggest benefit of a drill press over a regular hand drill, in addition to the fact that you know it's coming straight up and down, is that you can adjust the speed and you can make sure that you're using the proper speed for the right material, which will have a big effect on like the finish of your hole when you're done with it, or whether you're able to get through the material at all. So here's a recommended table of different speeds to set your drill press to. Setting the drill press speed is definitely something that a mentor should do. But mentors, you can reference this table and see what the best speed is for the specific material your students are working for, as well as the specific bit that you're using, whether it's a hole saw, a spade bit, or a standard twist bit. Here's a bunch of different speeds that you should set it to each material to give you the best result. As always, safety is extremely important. We don't want any of you getting hurt while you're working with these tools. And while you're being safe, it will also make the end result of your final piece better as well. If you're taking your time and you're thinking about what you're doing, what you create is going to be better than if you rushed it. And one good way that will aid in safety and also effectiveness is center punching holes you intend to drill. This is very, very relevant when you are using a hand drill because they have a tendency to walk as you are trying to drill holes, especially in things like the PVC pipe. So a center punch is just a piece of metal with a slightly sharpened tip that you can place where you intend to drill your hole and give it a quick tap. And this will put a dimple in where you want to put your hole that will allow you to keep your drill bit centered on it and drill easier. So on the PVC pipe, if you're doing it on part of the curve, it's a necessity. And it is also very, very helpful for the wood and the metal to make sure that your bit doesn't pop out. Just make sure you only hit it once. When you're center punching something, you want to hit it once so that it will put only a single dimple in. If you hit it more than once, it will jump up and down. And sometimes this can jump to a position just adjacent to where you wanted your punch initially. You'll have tool holes now, which defeats the whole purpose because then your drill may want to walk into the other one as you're drilling. So make sure you just hit it the one time, and that will give you the best result. You can also tap the aluminum blocks. So this allows you to put threads into the block and put a bolt in as if it were a nut. This is a hand process and is fairly advanced. Anybody can do it with practice. However, it's very, very easy to mess up. So you want to make sure that you get the proper tap number based on the hole size and the threading you're wanting to work with. So you really have to check what the size of the bolt you want to be threading it into and the number of threads per inch, the TPI that it has. You want to make sure you get an exact match. And you can get these from Ace Hardware as well as some other suppliers. So access is not the most difficult thing. However, when you are threading it, you want to go slowly. With the aluminum, you can get away without any kind of like cutting fluid because it's pretty soft. Just make sure you go slow. And every couple of turns, you want to make sure you back the thread, the tap out. The reason for this is because you're cutting through the material, you have scrap coming off. And if you just go the whole way through, that scrap will collect at the bottom of your hole. Unless you have a through hole. If you have a through hole, it's not as important. But if you don't, if you only have a hole that's going partially through the material, all the little scrap shavings will collect in the bottom, and your tap won't be able to force through them. So you'll actually end up cutting through the threads that you've already made because the tap can't go down any further. And this can mess up your threading very, very significantly. So make sure that you give it a couple twists and you back it out, and then you do the next 2 or 3 turns, and then just do that and take your time with it. Threading can make a lot of things really helpful, but at the same time, sometimes a nut is just the way to go. So if you need to thread something, it's possible. Just make sure that it is necessary. The foam is notoriously hard to work with. Not because it's hard to cut, mostly because it just gives you a really rough edge. So, hot knives or hot wires are underrated in my opinion for cutting things like the foam board, but it is dangerous. So, be careful with it. Make sure you don't burn yourself. Make sure you're staying away from the hot knife. And if it's deemed too dangerous, a regular knife will work just fine to cut through the foam board. It just may give you a rough edge. So make sure that's acceptable. And if not, you can have a mentor supervise you while you're using the hot knife. Just make sure that the student's doing the majority of the work and pre-drew what they intended cut. Last bit of kind of safety and recommendation that we'll go over for the electrical components. Make sure that all of your wires are securely fastened. And since in general adhesives are not allowed on returnable kit components, you want to make sure that your wires are secured. All too often, we've had teams who had something going to a manipulator or arm for a cord, and when they went to rotate, it got caught on something and unplugged the motor. And then you're basically dead for that match. So make sure that your wires are secured well. You can do that with tape or fasteners or other ways to make sure that the wire is flush and isn't going to get caught on something. And also make your Cortex easy to access. You'll be plugging things in and out to it a lot. You'll be unplugging the battery, plugging the battery in, connecting to it with the USB stick. So in general, make sure it's not somewhere that's super inaccessible because it will just make things a lot difficult. A lot more difficult and harder than they have to be. You also have limit switches as part of your kit. These are electronic switches that when you press upon one edge, it will uh, work as a switch. So it will either connect the current or let go of it. And you can put these in positions where you want them to be triggered. So Often they can be used if you want to have something that extends, but you only want to extend so far, and you want it to stop once you hit a specific point. Or perhaps on the exterior of your drive base when you come into contact with a game field piece. These are all really good ways of letting the cortex know that you are in contact with something. And as part of your program, you can have it do whatever you need it to do after that point. Whether it's stop, begin some other process, or whatever it needs to do, they can add a level of autonomy to your game, which is very helpful. You're also given a number of ways to mount your motor. There's a couple of ways that you can mount things to the motor, but you also need to be able to mount your motor to something. And the best way to do this is with the specifically designed mounting kits that Best provides. These are really good. They solve the problem for you. So it's one less thing that you have to think about. And they come flat, but they're designed to be bent. So you can do this in a vise or with one of the sheet metal bending hand tools we mentioned earlier, or in like a brake or something. Uh, but you can also do this just fine on a vise. So whatever works. Just make sure you don't bend it too much, and also understand that they are not going to bend back. Once you bend them, they are basically set in that shape. If you try and bend them out again, they're just going to fracture. And you get one bend out of this. So make sure that you bend the tabs in the way that you want them to go. You'll notice on the bottom half of these, there's tabs that have mounting holes in them. The large center hole is where the motor goes, and then you can bend those side tabs in, and then you have the other tabs, which you can go either on the interior or the exterior. I recommend on the exterior just because then when you put the bolts in, you're able to access the head. If you bend them onto the interior, the motor will be above them. And if you ever have to take those out, they can be a lot more difficult. You'd have to take the motor out to do so. However, if you are cramped for space, sometimes you got to put them on the inside. So just be aware of that and make sure that you are orienting the tabs in a way that will be most advantageous to you. I mentioned that you also have to attach things to the motors themselves. The motors have a slight cutout on them that allows you to put a set screw and attach something to them that will rotate with the motor. These are generally called hubs, and they are a central hole that goes around the shaft of the motor, but it has a bolt come in from one side that connects it to the motor itself. So we have this awesome demonstration from Englewood High School. So we're going to play that really quick about how you can construct your own motor hub to attach to the motor.
This is a robotic hub. This is what we're going to be making today. There's a hole in the center. There's also 4 holes on each corner. It's 2 by 2, and you have a hole up top. It's pretty simple. The first thing you're going to need to grab is an aluminum brick. You're also going to need to grab a speed square and a marker. Line up the aluminum brick with the most flush side to the ruler. You want this to be 2 by 2. So we're going to cut 2 inches. So this is where I'm going to mark it. So as you can see here, I have it marked at the 2-inch mark, which is going to give us a 2-inch square. Clamp the brick to the edge of a table. Now you use a different attachment on the grinder to smooth the edges. Now to put a hole in the center of the block, you're going to take a straight edge and draw an X. Simply put the straight edge corner to corner and draw a line. The center is going to be the most middle of the block. This is where you want to drill a hole. For the holes on the corner, you're going to want to mark in a 1/2 inch on each of the 4 corners. Where you drew that X a moment ago, you're going to want to drill directly into the center. You want to make sure that this hole is drilled all the way through. Apply drilling fluid if needed. Now you're going to drill the hole on the top. Simply line up with the hole in the center and drill through till you reach the center. Don't go further than this. This is all you need to do. Now you're going to be threading the holes. You want to make sure that you do not thread the hole in the very center. Apply a few drops of aluminum cutting fluid and make sure that the hole is clean of debris. You're going to drill in each hole except for the center, so the 4 on the sides and the 1 on the top. Place the thread in evenly. Turn the tap clockwise. You're going to do this until you feel pressure. It may take a while, but you're going to have to back out the thread every once in a while to clear it off of debris. As you can see here, I'm reversing it to pull it out and clean the threads off. Clean the hole again and then insert and turn clockwise again. Here's the finished product. This is your robotic hub. As you can see, you have your holes tapped where they need to be and it's ready for use.
And there you go. So motor hubs are generally the best way to attach something to one of the motors. Whether it's a wheel, it's a claw, it's another arm, whatever it is you're attaching, these wheel hubs make it a lot easier and are generally the best way to attach something to a motor. Here is a list of a lot of the resources stored at the link you can see above. So you can find a lot of resources relevant to the things that you're working with. So there's the consumable kit list, there was the returnable kit list, spec sheets for all your electrical components, a pinout diagram for the Cortex, a lot of great resources that will help you as you design and build your robot. So make sure that you check this out. And if you are wondering where you can find some of this information, you can find it above. You can also find additional information, including this presentation, this video, and all the other presentations and videos created for Kickoff as part of the BEST National Registry. So once again, you do need a BNR account and able to access all of that. However, they are great resources and definitely allow you to go over the things that were presented as Kickoff that you may have missed or want to reference again. That's it for me. That's robot design and construction tips. Once again, my name is Dakota Mann, and thank you all for watching. I hope you have a good rest of your day, and best of luck in the robotics competition to come. All right. Bye, everyone.